Alright, so welcome back to particle physics and the standard model. This is lecture 10 and this is going to be a special lecture. Okay, this will be slightly against the run of the narrative that we have been seeing. And the topic is an introduction to Feynman diagrams. Okay. I think now is the time for you to familiarize yourself a bit with these amazing illustrations of quantum field theory, amazing tools I should say actually, an amazing language of field theorists, Feynman diagrams. Okay. And I recommend that you follow along using Griffiths. There are any number of books that give a nice introduction, but Griffiths would do. Okay, I think this is in chapter 2 or something. All right. Why? Because we have been seeing all these particle processes, we have been applying them and studying their consequences arising out of discrete symmetries and so on, right. So, before we go to continuous symmetries and from there to field theory, it will be good to see, sometimes I drew these diagrams also, it will be good to see why I drew diagrams like these, what do these mean, how to think about these particle processes and so on. Okay. Okay, good. So, let us start. Okay. Let me just draw a few things here as an introduction. This you probably would see in Griffiths. Okay. What am I drawing here? This squiggly thing is a gluon. This is what I represent as a gluon. Okay. And if I have a gluon connected up with a couple of fermions, then necessarily those fermions have to be quarks. Okay. That is, the gluon is the mediator of the strong force or mediator of QCD, right. That means that when the quarks take part in the strong force, then you have to attach them to a gluon. Okay. This is one of the basic rules of drawing interaction vertices. Okay. Now, quarks, it turns out, also take part in the electroweak interactions. So, I can also draw a photon or a Z boson or a W. Okay. And I denote these other gauge bosons with this kind of a squiggle. Over here it looks like a spring, over here it looks like a squiggle, correct. Okay. So, there is one other thing that I have done here, right. I have drawn quarks with solid lines with arrows on them, right. That is how you denote a fermion. Okay. And what does the arrow mean exactly? We will see in a second. Okay. It has a very special significance. All right. Okay. Here is the thing. The things that I have drawn here are these Feynman diagrams? The answer is no, these are not Feynman diagrams. Okay. These are basically just the interactions allowed by the symmetries of your theory, in this case the standard model. Okay. So, what I have done is I have basically pictorially represented interactions in a Lagrangian in this form. So, these are just interaction vertices. Okay. The key word is vertex, these are vertices, not diagrams actually. It is a diagram in the English sense, but not in the physics sense, it is not a Feynman diagram, okay. It is an interaction vertex. Okay. So, I can draw this in any orientation I want. So, for instance, the same thing I can draw like this. Okay. The arrow means nothing here, the fermionic arrow. Okay. I can draw same diagram like this also. Okay. Okay. Now, can I ever have a diagram like this? Is this valid? It seems like I am just taking Lego blocks and putting them together whichever way I want, right? So, as long as I do that, can I do this? Again, it turns out no, absolutely not. This is absolutely invalid. Why is that? Okay, there are many things that are being violated here, alright. So, let us say if these two are photons and this is a fermion and the fermion carries charge, then at the vertex charge is not conserved, right. But even more importantly, even if you arrange the electric charges and other things to be fine, the fermion carries a spin, right. So, this is a spin half particle and this is spin 1 and this is spin 1. So, there is no conservation of spin here. So, look at the diagram above carefully. There were two fermions that were connected up to a spin 1 a boson, right. So, that was fine. Okay. I could even do this, I can connect two fermions to a scalar particle. Okay. This is how you draw scalars with a dashed line, right. So, this is spin 0, this is spin 1, this could be a W or a Z or a photon, and this is also spin 1, a gluon. Okay. These conserve spin, but this does not, right. So, no, so I cannot do this, this is not allowed. Okay. How about this? Again, for the same reason, this is even more absurd, right. For the same reason, absolutely not allowed, this vertex, alright. Okay, good. So, you have to make sure that all the spins and charges and other things are conserved at the vertex. Okay. Now, let me go to some more non-trivial diagrams. What about this? Can I ever have this? Three gluons connected up together? Well, first of all, it is allowed as far as spin is concerned, right. You can join up three spin 1 particles and then make sure that spin is conserved, right. When I add up the spins of two spin 1 particles, there is a possibility of getting another spin 1 particle, right. This is from quantum mechanics, how you add spins and angular momentum, correct. So, it is allowed as far as spins are concerned. It turns out that due to the gauge structure, again not a term that you might be familiar with right now, we will see this, okay, of QCD, this actually is allowed, okay, for gluons. Similarly, I can even have a 4 gluon vertex, that is also allowed by gauge structure. It is also allowed by spin and other things, obviously, right. It is also allowed, by the way, by color charges. Gluons carry a QCD charge in addition to regular, it is electrically neutral, but in addition to electric charge there are things like color charges which arise in QCD, and gluons carry this charge, and it turns out that color charge is also conserved in these vertices. Okay. Now, the reason I bring that up is that I cannot do the same thing for photons. A 3 photon vertex, and for that matter a 4 photon vertex do not exist, and that comes from the gauge structure of electromagnetism. Okay. So, this might seem like a rule that I just imposed on you suddenly, right, but bear with me, I am just trying to illustrate that when you draw Feynman diagrams and when you draw interaction vertices out of which these are made of, not everything is allowed, okay. These are not arbitrary things, there are very specific rules that you need to follow, and one of them is whether charges and spins and other things are conserved at the interaction vertices, and that is imposed upon by the symmetries of the theory. Okay, just keep this in mind. We will explore all this in glorious detail when we get to the field theory aspects and put them back to Feynman diagrams. Okay. Now, what about, just to make things a little more confusing, what about this vertex made up of weak bosons like the W and the Z? Turns out that is allowed. Okay. Just to complete this section, this is also allowed. This could be a photon or a Z, and even having 4 W's, these are all allowed, turns out. Okay, it's just that you can't connect up just photons. Okay, eventually we will see, for the experts, we will see that this has to do with the fact that weak interactions are also described by a non-abelian gauge group. Okay, that is what makes the difference, abelian versus non-abelian. Okay, but yeah, just to drive home the point that there is nothing arbitrary about these diagrams. Okay, they follow very strict rules. Okay, if these are interaction structures, if these are just pictorial representations of interactions in a Lagrangian, then what are Feynman diagrams then? Okay. What is really a Feynman diagram? What is the Feynman diagram depicting? What is the physical significance? What is the physical meaning? Alright. A Feynman diagram is a pictorial representation of a transition amplitude. Have you heard of this term? If not, go back to your quantum mechanics course and look at this. You must have seen transition amplitudes from one state to another, right, and from which you get Fermi's golden rule and so on, right. So, it represents the transition from some in state in the transition to an out state, and I have sandwiched that with this operator, right, the T is standing for transition, right, good, and that is denoted by, usually denoted by M. M is the symbol that we use for the transition amplitude when we go from some state to another. Just to give a concrete example, if you want to go from you take an E plus E minus as the initial state, and then you want to end up with a QQ bar, an up quark and anti up quark. Okay, then the in state is the E plus E minus, and the out state is QQ bar. Now you want to calculate what is the probability of this happening in some setup, for which you need a quantum probability amplitude. That is the transition amplitude. Okay, this is the basis that you this is the most basic thing that you use to calculate things like cross sections, decay rates and so on. Okay. All right. So, once I put it this way, we know that in quantum mechanics amplitudes add, correct. If there is more than one path, right, in the path integral, for instance, for something to happen, then you have to add up the probability amplitudes, correct. You do not add the probabilities, you add the probability amplitudes, right. That is the most basic thing about quantum mechanics, correct. So, that means all possible paths in the transition must be accounted for. Okay. So, in a certain process, if I want to go from some initial state to final state, I have to account for everything that is possible that is given by the Lagrangian. Okay, and we will see how what this means in a pictorial form. Okay. Now, One mistake that a lot of students make about Feynman diagrams is that, let me draw a Feynman diagram to illustrate what I mean. Let us take the process that I just talked about, E minus, E plus, and then let me exchange a photon, and I have a quark and an antiquark. Okay. One common mistake that people make about Feynman diagrams, a common misconception, is that this literally represents an electron and a positron coming together and then literally exchanging a photon, and then the photon travels a distance and it splits into a quark and an antiquark. Okay? Now that is completely wrong. That is absolutely not what the Feynman diagram is telling you. Okay? Because a Feynman diagram is not a representation in real space. No, not in real space. Okay? It is actually a representation in, so to speak, momentum space. Okay? In other words, the diagram that I have drawn here, right, all of this is happening at one single point in space time. In fact, one single point in space, let us say. Okay? Remember, these are graphical representations of the transition amplitude, right? Nothing to do with actually two particles coming together and then creating a track in some bubble chamber or something like that, nothing like that. Those are just particle tracks. You can represent them also pictorially, but that is not a Feynman diagram, that is different, that is just a particle track, a real track actually. This is something else, this is a more quantum mechanical concept. Okay? So, okay, having said that, you may have encountered this, if not this is where you encounter it. When we draw Feynman diagram, when we draw these amplitudes, we fix the direction of time. You will see this in Griffiths also. Okay? We say that time goes from left to right, and then I have Q bar production, and you know, I can either draw my Feynman diagram in this direction, or sometimes you can fix the time in the horizontal, sorry, in the vertical direction. In that case, you say that you know, this is how you draw the Feynman diagram, right? These two are exactly equivalent, right? But the reason you fix the time direction is that if not for that, one might mistake the right hand process to be a quark hitting an electron and then giving an anti-quark and a positron. Just to denote that, we fix the direction of the time to tell you to say exactly what process it is. Okay? Basically, when we fix the time direction, it is to distinguish the in versus out state. That is what this means. Does not mean that in time these two particles are getting together and then they form a photon, that the photon travels a distance and splits away. That is not what it really means. This is more for psychological convenience. Okay. Fixing the direction of time in the Feynman diagram, just to tell you what is the in state versus out state. Okay. I generally like this convention of fixing time to go in the right direction, right hand direction, so that I can literally see that on the left, you know, is where the in state is, on the right is where the out state is. This is more intuitive to me. For some other people, bottom is the in state and up is the out state, and even the other way around and so on. Okay. In this course, we will follow left right convention. Okay. Here one other thing I want to add is that this is where the concept of the fermion arrow comes in. right. So for a fermion I said there is an arrow, right, and you would have noticed that whenever I drove a positron or an antiquark, I was putting the arrow in the other direction on the line, correct. This I do assuming that time is fixed on the Feynman diagram in this direction, okay. And this goes back to the statement we were making when talking about the CPT theorem's proof that a particle going in a forward direction in time is equivalent to an antiparticle moving backward in time, right. So this is kind of a pictorial representation of that. It is not quite that. There are things like fermion numbers and so on, but you can think of this convention having to do with that, okay. For an anti-fermion I am drawing the arrow in the opposite direction, okay. All right, so I will just leave it there for as far as fermion arrows are concerned, okay. What else? Good. So, all right. So, we talked about how the total amplitude is the sum of the amplitudes because it had to take up all paths, right. So, now let us see what I mean by that in pictorially. Let us take this process again, okay. E plus E minus going to Q bar. I can then draw this, of course, but can you think of any other way to have E plus E minus in the initial state and Q bar in the final state? Was there any other particle that can do this, that can do the mediation? Turns out there is. That is the Z boson. Okay, usually the rule of thumb is whenever you see a photon, right, you can also replace it with a Z boson. This has to do with how electroweak symmetry breaks, but for now just remember this rule. Every time you see a photon, it is okay to replace it with a Z boson, okay. So the total amplitude, when I want to calculate it, I cannot just take the first one, I have to add them both. I have to make use of both paths, and that is what ultimately tells me the amplitude and hence the rates and so on, okay. There is another sense in which this is true, okay. This is one sense in which this is true. There is another sense. So without changing the mediator, all right, suppose I have an E plus or E, electron positron, I am now exchanging another electron in this fashion and I make 2 photons, okay. Can I draw another diagram that gives me E plus E minus going to gamma gamma in the final state? Is there any other diagram that I can draw given that the only vertex allowed is this vertex, right? That is the same vertex I have drawn here also, right, an E gamma vertex. This is a bit hard to answer, but here is what one can do, okay. What I can do is, once again I can exchange an electron in this channel, but in the final state I am going to swap the 2 photons. See, the photon over here that I drew up here is now coming down and then this photon is crossing over that other photon, okay. And these 2 diagrams are actually distinct from each other, okay. I can call this amplitude M1 and I can call this amplitude M2. They are absolutely distinct from each other. Why? Because, and this is what I wanted to illustrate, again remember these are representations of the transition amplitude in momentum space, right. That means I have to work with momentum labels, correct. In other words, I can assign this state momentum P1, let me call this P2, I will call this P3 and I will call this P4. Okay. So, in the final states I am also fixing the momentum labels, right, which means once again here I cannot change the momentum labels, I cannot change the ordering in which I label the momenta. So, this photon which had momentum P4 can also have a momentum P3, that is what I have done here, right, and similarly this photon which had a momentum P3 can also have a momentum P4, and these are two different amplitudes, right, in momentum space, correct, but these two are also allowed, these are again two distinct paths by which an E plus E minus can go to gamma gamma. So, I have to treat them both separately. Okay, this is what we mean by all paths must be pictorially represented. As long as you satisfy conservation laws at the interaction vertices, you have to draw all the paths that are possible. Okay. All right, and you know, not just you can switch the momentum labels, you can put in all the mediators that you want, but you have to account for all of them. That is what gives you the full amplitude. Okay. Having said that, this statement has one more connotation. You can also make loops in these diagrams to get all the paths possible. Okay. What do I mean? Once again, let us take E plus E minus going to Q Q bar. I can not only draw this diagram, I can also draw diagrams like these. Once again, I have in the initial state I have this, a photon. Now, the photon itself, right, can go to say a mu plus mu minus, let us say. Totally possible, right? If gamma connects to E plus E minus, you can go to mu plus mu minus also, and I connect it up with another photon. Basically, I have split this into mu plus mu minus, and then they recombine to another photon, or you know, why should I go for a photon? I can also have a Z here, right? And that has now gone to a Q bar. Absolutely possible, absolutely allowed by all the conservation laws, right? So, this also has to be accounted for. Okay. If in that case it is not just mu minus mu plus, right, a photon can split into say an up quark and an anti up quark and so on. The photon can split can connect to any fermion anti fermion pair as long as those fermions are charged under electromagnetism, correct. So, there seem to be an endless number of possibilities that you can draw here, right. This could also be a Z on the left hand side, for instance, correct. But I can't stop just there, I can go even further. Why should I draw a loop only on the you know, photon or the Z boson that is being exchanged? I can draw a loop here also. Let me show you. Let me go to the next page and show you. No, I'll just do it in the previous page. So, I can you know, can have an electron, and over here, right, this positron can split into a photon or a Z boson, right, and another positron. This vertex is exactly the same vertex that we have been drawing all over the place, right. This vertex is the same as this vertex, correct. So, that this is also totally possible, right, and over here I can just exchange a gamma or a Z and I get a Q bar. I could have drawn this loop on the electron also, or I could have drawn a similar loop on one of the quark legs or the anti-quark legs, right. So, all of this is possible, right. In fact, I can combine these two. So, these have one loop in them, right, but I can also have two loops. I can combine these two, I can have a loop on the leg, I can have a loop on the mediator and so on, right. So, it seems like we have a big headache here to actually get the amplitude. we seem to be adding infinite number of Feynman diagrams here, right. So, how do we even solve anything here? How do we even compute the amplitudes or rates of any processes? Well, we have to remember that at every vertex, right, it is not just a vertex, those vertices in the amplitude calculation come with coupling constants, usually denoted by some G. They come with some coupling constant that is usually a number that is smaller than 1. Okay. That means in this diagram, in this first loop diagram, I have 1, 2, 3, 4, there are 4 coupling constants. So, it is roughly proportional to G to the 4th, right. This also has 4 coupling constants. Whereas this diagram, I am going to give this diagram a name now. This is called a tree diagram as opposed to a loop diagram. Okay. So, in this tree diagram, the amplitude is proportional to only G squared, and G squared is larger than G to the 4th, right, as long as G is less than 1. And it turns out that nature has been kind enough to make a lot of the coupling constants that we work with smaller than 1. There are certain cases where it is larger than 1 and makes it a big pain in the neck, but you do have cases where most cases are smaller than 1. So, you can do perturbative expansions of the amplitude and order amplitudes into tree diagrams and loop diagrams. And in most cases it turns out that only the tree diagrams contribute the most, or only the tree diagrams actually matter, okay, because they contribute the most, they dominate the amplitude. Okay. So, I will stop around here. I think we have seen a lot of concepts involved in Feynman diagrams. There is a couple more subtleties that we need to explore, which I will do in the next lecture before we take up continuous symmetries on the way to gauge theories. Okay? All right. Thank you.